Hello everyone and welcome back. Today we'll be starting off with chapter 5 of AI and Machine Learning for Coders by Laurence Moroney. In chapter 5 we'll be learning about Introduction to Natural Language Processing or short for NLP. So, it is a technique in artificial intelligence that deals with the understanding of human based language. It involves programming techniques to create a model that can understand language, classify content, and even generate and create new compositions in human based language. We'll be exploring these techniques over the next few chapters. So, there are also lots of services that NLP can create to create applications such as the chatbots, but that's not in the scope of this book. So instead, we'll be looking at the foundations of NLP and how to model language so that it can train neural networks to understand and classify text. For a little fun, you'll also see how to use predictive elements of a machine learning model to write some poetry. So let's get started. First, we'll be understanding how encoding of language into numbers is done. So you can encode language into numbers in many ways. The most common is to encode by letters. So as it's done naturally when strings are stored in a program, in your program. In memory, however, you don't store the letter A but an encoding of it, perhaps an ASCII or Unicode value or something else. For example, consider the word listen. So it's encoded in ASCII into the numbers 76, 73, 83, 84, 69 and 78. So as we can see that the word listen here has, let us count, 1, 2, 3, 4, 5, 6 alphabets, right? And there are 6 numbers that are used to represent it or encode it into the ASCII language, right? This is good in that you can now use numerics to represent the word. But consider the word silent. It's an antigram of listen. The same numbers are represented in that word. So what's here is that S is also available in silent. It's also present in listen. I is also present in silent. It's also present in listen. So we can say that all the words in silent are also available in listen. So the alphabets of silent and listen are same. That means same number would be used to encode these two words, right? That even though their arrangement would be different, but same numbers are used. So that's a problem over there. So what's a antigram? If you don't have any idea about antigram, an antigram is a word that's an anagram of another but has the opposite meaning. So for example, united and untied are antigrams, and as are restful and fluster, Santa and Saturn, 45 and over 50 are antigrams, right? So let's just skip this ahead. A better alternative might be to use numbers to encode entire words instead of letters. So instead we say silent represent the alphabet of silent separately as numbers. We'll just say that we'll represent silent with the number X and listen with the number Y. So they won't overlap, right? Using this technique, let's consider a sentence like I love my dog. So if we denote I with 1, love with 2, my with 3 and dog with 4, it means that the sentence I love my dog can be encoded as 1, 2, 3 and 4. If you then wanted to encode I love my cat, it would be I for 1, love for 2, my for 3 and cat for 5, because 4 is already representing dog. You've already gotten to a point where you can tell that these sentences have a similar meaning because they are similar numerically, right? So 1, 2, 3, 4 and 1, 2, 3, 5 looks numerically similar. This process is called tokenization. So basically what we are going to do is we're going to assign some tokens to each word in a sentence. Let's get started with tokenization, and there is a library called Tokenizer in TensorFlow Keras, and for getting that we need a library called preprocessing that provides a number of useful tools to prepare data for machine learning. One of these tools is a tokenizer that will allow you to take words and turn them into tokens. So let's see how it works. As it is, we are importing TensorFlow and Keras, and from Keras we are importing preprocessing text.import tokenizer. Then there are two sentences you can see. Today is sunny day, today is a rainy day. Tokenizer is equals to tokenizer, that tool that we are using, and number of words equals 100. Then we just fit on text with this tokenizer the sentences that we have, and finally we get the word index. So which index is donating which word, we are just printing it down. So let's see the output. So in the red line you can see today is denoted by 1, is denoted by 2, is denoted by 3, day is denoted by 4, sunny is denoted by 5, and rainy is denoted by 6. In this case, we create a tokenizer object and specify the number of words that it can tokenize. This will be the maximum number of tokens to generate from corpus of words. We have a very small corpus here containing only 6 unique words. So we'll be well under the 100 specified. So it depends upon the number of words in a sentence. So num underscore words is actually denoting what will be the maximum number of tokens that it has to generate. The tokenizer has to generate. So once we have a tokenizer, calling fit underscore on text will create the tokenized word index, and we'll print those out as you can see in the red text. The tokenizer is quite flexible. For example, if we expand the corpus with another sentence containing the word today, but with a question mark after it, the results show that it would be smart enough to filter out today question mark and just today. So basically what we're doing here is we are removing any punctuation because it does not mean anything for the code, right? So what we're doing here is we have added another line in the sentences that it is sunny today question mark. So as you can see in the output, we are not getting question mark as any key or value for the key. This behavior is controlled by the filters parameter to the tokenizer, which defaults to removing all punctuation except the apostrophe character. So it removes all the punctuation except the apostrophe. So for example, today is a sunny day would become a sequence containing 1, 2, 3, 4, 5, and with preceding encodings and is it sunny today will become 2741, right? Once you have the words in your sentences tokenized, the next step is to convert your sentences into a list of numbers, with number being value where the word is the key. So number is the value and the word is the key. Turning sentences into sequences. So now we have the words and we have encoded them into numbers. Now it's time to turn these sentences into sequences of numbers. Right. Now that you've seen how to take words and tokenize them into numbers, the next step is to encode the sentences into sequences of numbers. The tokenizer has a method called text underscore to underscore sequences. So we are converting sentences into sequences using text to sequences. All you have to do is pass your list of sentences and it will give you back a list of sequences. So sentences here, and in the code you can see we've given the sentences we have called the tokenizer with maximum number of words is 100, that the number of maximum tokens, that's the maximum number of tokens that it has to issue. And then we use fit on text with sentences, and finally we use tokenizer.word index to get the word index of each word. And here we are using text to sequences, and we are passing in the sentences so that we get the sequence here. So finally the output will look like something this, and we have the sequence of numbers here. You can then substitute in the words for the numbers, and you'll see that the sentences make sense, right? So let's just try for the last one. So 2741. So 2 comes in for is, 7 comes in for it, 4 comes in for sunny, is it sunny, and 1 comes in for today. So it says is it sunny today. Now consider what happens if you are training a neural network on set of data. The typical pattern is that you have a set of data used for training that you know won't cover 100% of your needs, but you hope you cover as much as possible. In the case of NLP, you might have many thousands of words in your training data used in many different contexts. But you can't have every possible word in every possible context. So, when you show your neural network some new previously unseen text containing previously unseen words, what might happen? So, as you've guessed, that if our training data contains some data that it hasn't seen before, and it does not have any context with that, and it contains a lot of unseen previous words, so we might say that it will get confused because it simply has no context for whose words, and as a result any prediction it gives will be negatively affected. So how do we use that? So how do we tackle with the unseen words that our machine hasn't seen before, or our model hasn't seen before? So for that we use out of vocabulary tokens. So what is out of vocabulary token is that to handle these kind of unseen texts or unseen words, we use this token. This can help your neural network to understand the context of data previously containing previously unseen text. For example, given the previous small example corpus, suppose you want to process sentences like these. So our test set is today is a snowy day. Will it be rainy tomorrow? So our previous test or training data does not have the word snowy or tomorrow. Remember that you're not adding this input to corpus of existing text or the training data, but considering how a pre-trained network might view this text. If you tokenize it with the words that you've already used and your existing tokenizer like this. So when we use text to sequences, we've converted this text data sequence into sequence in sentences into sequences. So let's see what's the output like. So word index would look like something this. So as you can see for the data, the test data looks like 1, 2, 3, 5 and 7, 6. So if we take in consideration 7 and 6 and we go reverse allocation, we do reversing here, its meaning is for 7 it is it, for 6 it's rainy. So our actual sentence was will it be rainy tomorrow, but our actual sentence became after training it rainy. That has no meaning. So right, so what we are going to do here is we are going to remove and use out of vocabulary token here to specify it in the tokenizer. So for that you can just add a parameter called OOV underscore token. Right, let's see how it's using. So tokenizer equals number of words 100 and OOV underscore token is equals to OOV in brackets. The rest of the else is all same, and when you run this code you will see that the output is now OOV for one. So whenever there is a word that it does not know, it uses one over there, and it is reserved for OOV, that is out of vocabulary text. So now our final word will become, so we were looking at the second one, right? So 111871. So the sentence becomes OOV. For it is it, OOV, then it's rainy, it, OOV rainy, and OOV. So it is much better than the for the last one, because it was not actually giving any words. At least in this we have an idea that there are some words in place of OOV. This tokens has a new item OOV, and your test sentences maintain their length. So the original length of the sentence is maintained here. Reverse encoding them will now give today is a OOV day and OOV it, OOV rainy, OOV. The former is much closer to the original meaning. The latter becomes most of all its words aren't in the corpus, still lacks a lot of context, but it's a step in the right direction. Next, let's understand what's padding. So, when you're training neural network, you typically need all the data to be in the same shape. You remember the time when we changed the shape and size of the input images to 300, 300, because that was the input requirement for our model. The same has to be done in case of sentences and words. Recall from earlier chapters that when training with images, you reformatted the images to the same width and height. With text, you face the same issue. Once you've tokenized your words and converted into sentences into a sequence, they can all be of different lengths. To get them to be same shape and size, you use padding. So the padding takes place after you've converted your sentences into a sequence of numbers. So here are the sentences. There are 4 sentences, each of different length. And as you can see, when you get the sequence length, we can see the first and the second sequence are similar length. The third one is one short. The fourth one is bigger than the rest of them. So there is a difference here. When you print the sequences, they'll all be in the single line. So these all sequences that you've already just seen now, they'll be in the single line, but the author has broken them into parts. If you want to make these the same length, you can use pad underscore sequences API. So if you want to just make them of same shape or length, you have to use pad sequences API. So you have to just import it using pre-processing and dot sequence and just import that. Then use padded equals pad underscore sequences and pass in the sequence. And when you'll print it, it will be all padded. You'll get a nicely formatted set of sequences. They'll also be on separate lines, right? So here you can see that they are formally padded. The sequence get padded with 0, which isn't a token in the word list. So if you had a question that why the sequences were starting with 1, here is a thing that we always pad our sequence with zeros. Now you have something that's regularly shaped, and you can use this for training. But before going there, let's explore this API a little because it gives us many options. So first of all, if you had noticed in this case of shorter sentences, to get them to be the same shape as the longest one, the requisite number of zeros are added in the beginning. That's called pre-padding. But if you want that the number of zeros are added after the sequence, we can also use that. So what we're going to do is we are doing instead of going for pre-padding, we'll be going for post-padding. So for post padding, just add padding equals post, and the zeros will be shifted after the sequence. You can see that now the words are at the beginning of the padded sequences and the 0 characters are at the end. The next default behavior you may have observed is that sequences were all made to be the same length as the longest one. So what's happening here is actually we are trying to make the shape of all the sequences that we have equal to the shape of the longest one. It's a sensible default because it means you won't lose any data. But if there is still some scope that you want the shape of the longest one to be equal to the shape of the smallest one, you can also do that a lot. But that will lose your a lot of data. So what you can do here is you can just specify the maximum length parameter and just specify it equal to the 6 or any number that length you want. Right. Now your padded sequences are all the same length and there isn't too much padding. Right. You can see the number of zeros have decreased. You have lost words, some words actually, from your longest sentence, though they have been truncated from the beginning. So they have been removed from the beginning. But if you want you want to lose the words from the beginning, instead you want them to be removed from the end of the sentence, so you just have to use truncating equals post. The result of this will show that the longest sentence is now truncated at the end instead of the beginning. Now let's just get started with some code. This is the whole code that I've already written from the book until the point that we have read. So I've covered the basics, tokenizer and padding. So let's just get started and run this. So we are importing the basic imports. Here are my 4 sentences. So the tokenizer, number of words I've specified as 100. So fit on text sentences and the tokenizer dot word index. So it will return me the word index. You can see today has an index of 1, is has index of 2, has index of 3, sunny has index of 4, and day has index of 5, and so on. And I want to make sure that in coming videos we'll also know how we can remove these is from the list, because these come in very frequently in the sentences and they don't really add such value to the sentences as the words like today, sunny, rainy, or day, right? So we'll try and remove these also, and then let's just convert the sentences into numbers or sequences using text to sequences. And here is my sequence. So you can see that today is a sunny day is encoded as 1 2 3 4 5. Today is a rainy day is encoded as 1 2 3 6 5, and it's a sunny today, is it sunny today, is encoded as 2 7 4 1. For previously unseen data, that was the test data that we're thinking about. And here it is that today is 1, is 2, is 3, sunny is 4, day is 5. It's almost similar only, but the question mark does not have any value here. So the question mark does not come, that's the punctuation, right? So let's just get started and see that 7 and 6 here for will it be rainy tomorrow, but if we swap back the tokens we won't get the same thing. So let's see, for 7 it is it, for 6 it is rainy. So the sentence would be it rainy, but the actual sentence is will it be rainy tomorrow, right? So we did not get the actual sentence back. But what will be about the out of token words? So for the test data, that words that we were not expecting and were not part of our training data, what about them? So you can see that OOV comes at 1, and we also notice that our index does not start with 0, it always starts with 1 here. Now reverse encoding, you will actually get it rainy, which is much better than this one, earlier one, right? So it was it rainy, but if you can actually see here, I've also written OOV here. This is the actual line or sentence that you'll get. Next, we are just trying some padding over here, that I've added padding equals tf.keras.preprocessing.sequence dot pad underscore sequences, and it's true, and we can just try to truncate them equals, let's try post, right? I think it will be truncating, right? Truncating, and let me add some padding equals post. So let's just try and run this. Yes, you can see there is some difference, and you can see the padding is now post as it was previous, and similarly you can see the truncating is also post, and you can see the words have been disappeared from the back rather than from the front, right? So that's it. I hope that is the most easiest part, and you can easily learn that. You can understand these and you can try it for yourself. You will get the code for this in our GitHub only, and I have also linked it in the below the video in the description. You can just go ahead and check this out. Just run this collab by yourself, and next we'll be going through some of the IMDb datasets or some public datasets and try out these all things on that, and try to convert or encode and embed these sentences into sequences of numbers so that we can play better with them. So thank you so much for joining in.